Assalamu alaikum. In this video, let's look about wave-particle duality of matter. Wave-particle duality of matter. We know that the interference, diffraction, and polarization are evidence of wave nature of light. We have studied about these characteristics in waves and oscillation, unit number 3. There, we have explained them. We have explained how interference occurs, how diffraction occurs, and how polarization occurs by considering light as a wave. But later, we discuss about the photoelectric effect, the blackbody radiation, and in your chemistry, you might have discussed about the atomic line spectrum, and these they cannot be explained using the wave nature of light. They are explained using a term called photons. So those photons, they are the evidence of particle nature of light. So it's clear that the interference of light cannot be explained using particle nature, and photoelectric emission cannot be explained using wave nature. Therefore, light is sometimes behaving as a particle, otherwise behaving as a wave. Therefore, we say that light has wave and particle nature. Therefore, we call this one as dual nature. Then, what's this de Broglie's hypothesis? He says, just like light, matter also should have both the nature. It should have a particle nature and as well as it should have a wave nature. But when he made this hypothesis, he didn't have any evidence. He just says that it should behave like light. It may be similar to light. That is why we say hypothesis. But his hypothesis didn't have any evidence to support his idea. It was just his statement. So de Broglie hypothesis says that matter consists of both particle and nature, particle nature as well as wave nature. Every moving particle has a wave associated with it. So that's his statement, de Broglie hypothesis. So according to his statement, he also obtained an equation that the wavelength of such wave is Planck's constant divided by the momentum. In terms of kinetic energy, let's try to get this equation in terms of kinetic energy. We know that kinetic energy is equal to half mv squared. Here we are talking about matter, therefore it will have a mass as well as a velocity. So P is equal to mv. We know momentum is mass into the product of velocity. We can write energy as E is equal P squared over 2m. So we obtain that momentum is root of 2me, but lambda is hp. Therefore, let's replace p in this equation with this. So we get an equation for this matter waves in terms of energy, in terms of kinetic energy. If you're wondering how we got this equation, we know that E is equal half mv squared. Introduce m up and down. So we get m squared over v squared over m. So this one could be taken as mv whole thing squared. So we have E is equal half mv whole thing squared over m. So replace this with p squared over 2m. That is equal to E. So now we know that P squared is equal to 2me, therefore P is equal to square root of 2me. If we take macroscopic particles that we can observe, so those particles, P is high, momentum is high, because we know P is equal mv. When mass is high, momentum is high. So, according to this equation, when momentum is high, lambda is very low and not measurable. For microscopic particles, electron, proton, neutron, avoid photon for now, it can be included. Electron, proton, and neutron, we are talking about microscopic particles. P is less because their mass is very less and they might have considerable velocity, but compared to that, their mass is very less. Their mass is very less, therefore, P will reduce. When P is less, lambda is significant and measurable in the order of nanometers. So the wave associated with moving particle, it is not an electromagnetic wave, it is not any type of wave that we have discussed earlier. We call this one as matter waves. Although de Broglie came up with this hypothesis without any evidence, later in an experiment carried out by two scientists, C.J. Davidson and L.H. Germer, and also by a similar experiment carried out by G.P. Thomson, son of J.J. Thomson. They observed that wave particle wave particle nature of electron was observed, and the theory, de Broglie's theory, was confirmed. So we know that electron is a particle, but it is showing wave-like property. So what's the experiment they conducted? The experiment they did was uh, electron diffraction. Electron diffraction. So it's just like this. Now, we know that electrons are particles. And just think, if we have a grill-like structure, so we have a grill-like structure, if we shoot electrons towards this, then what has to happen is, if electrons were particles, they just have to pass through, and in the screen behind, we should get the same pattern. Maybe this is a scintillating material, so where the electron hits, we must be able to observe, and we should get the same pattern of this grill. But instead, what they observed was the electrons is deviating, diffracting. So now the experiment is like this. We have a similar structure, but that's very small. So we know that when wave passes through an edge, it will diffract. It will diffract. So and as well as when wave passes through small slit, they diffract just like this. And if they start to diffract, they will produce now the electron moving through will diffract. Okay, this is the screen behind. I'll draw the screen properly. Now let's say this is the screen behind, and somewhere here we have that grill-like structure. Actually, it is an ionic atom, because in ionic atom we naturally get this grid-like structure. because they have a definite shape. And when electrons are sent through this, they start to diffract. Instead of moving straight, they diffract. They diffract in all direction, and uh, we can observe rings, rings like structure or rings like scintillation in this material, because when they diffract, they have a certain lambda, certain wavelength, and when they diffract in every direction from the center, it will produce a circle-like structure. So, you don't need to know the experiment in detail, but I'll show a YouTube link. You can check it. Look, this is what we expected. Nothing interesting. It should be obtained in the shape just like this grid in front, but the obtained shape is like this. Therefore, it has undergone diffraction, which is a characteristic of a wave. Therefore, these electrons should have act like waves. So, de Broglie's hypothesis was proved with this experiment. So the experiment, by aiming an electron beam moving at an constant speed towards a thin metallic foil or metal, a diffraction pattern can be observed on a screen. And that pattern is similar to that of X-rays. This was shown by Thomson. So we know that X-rays are wave nature of wave nature. They are waves, and electrons, it is matter. Both of them show the same pattern. That means electron has behaved like a wave. Hope the idea is clear. You don't need to understand that experiment in detail. If you understood this point, you should be able to get it. The electron created a certain pattern, and the same pattern is created by X-rays. Then both of them should have acted similar. That means electron has acted just like a wave. And the electron microscope is an example of application of wave nature of electrons. You can just search how the electron microscope works. So that's all about wave nature of dual wave particle duality of matter. So in a summary, if I say de Broglie thinks about the light's wave and particle nature. Therefore, he comes up with an idea that matter also should have both wave particle nature. And according to his equation, those having high momentum has very low wavelength, which is not observable. But with less momentum, lambda is high. For small particles, lambda is observable. Although this was a hypothesis, there was no any experiments to prove his claim. Later, two scientists and G.P. Thomson separately, they did a few experiments which could be only explained if electron was considered as a wave, because X-rays, which is a wave, also gave the same pattern. Therefore, de Broglie's hypothesis was proved. So that's the summary. Assalamu alaikum.